In this lecture, I'm going to formally introduce subspaces. We talked about them in the previous lecture, but I'll give you the actual definition here. Then we'll go over some examples, and then I'm going to talk about something called a spanning set, which is an important concept in linear algebra. A subspace of a vector space is a subset of a vector space, which is also a vector space in its own right. We have a very simple example. Every vector space has a subspace, namely the empty set. That's by definition. And we also saw several examples in the previous lesson. For example, number 3, where we had all multiples of a vector through the origin, which was essentially a line in n-dimensional space. That was a vector space. Another example would be, let me point to it here, if we have m less than n, then Rm is a subspace of Rn. This follows since we know that Rm is a vector space in its own right, and clearly it's a subset of Rn. So for example, if we start with, say, three-dimensional Euclidean space R3, then R2 is a subspace of R3, and R1 is a subspace of R2. It's also a subspace of R3. In fact, there's multiple isomorphic two-dimensional subspaces in Rn, but we'll get to that later. Let's take the set P of all triples x, y, z in R3 such that x minus 1/2 y plus z equals 0. So by definition, P is a subset of R3, but we want to show that it's also a subspace. So let's try to quantify this condition a little bit better here. We can solve for y in terms of x and z, which I've done here. So y equals 2x plus 2z. Then we can plug that back into our triple. So we'll have x and then y in terms of x and z, and then we'll just put in our z. Then we can write this as x times the vector 1, 2, 0, there's no x in this last term, plus z times 0, 2, and 1. And so our set P can be described as the set of all linear combinations of the vector 1, 2, 0 and the vector 0, 2, 1, which I've stated here. So this is actually a plane. It goes through R3. You can see if you make x and z equal 0, then the 0 element is in our set P. We're free to choose x and z however we like. So let's continue with the example in the next slide. I wrote our formula here at the top that we derived on the previous slide. So we want to show the rest of the axioms for a vector space for our set P. We already showed there was 0. We can show it again here. If you just take x and y, x and z equals 0, then this gives you the 0 vector. So that's in there. The additive inverse is pretty easy. So if x, y, and z is in our set P, we just take minus x minus y minus z, and then using this formula here, we get minus x times 1, 2, 0 minus y times 0, 2, 1. So it is a linear combination of the two vectors. In other words, the inverse is in P if x, y, and z is in P. Then we'll look at the two closure properties. The sum of two vectors that are a linear combination of these two vectors can also be represented as a linear combination. I didn't write it out, but if you have like one vector in P, in our set P, you can take it as x sub 1 times this vector plus z sub 1 times this vector, and then x sub 2 for the other element in P, x sub 2 times this vector plus z sub 2. And then when you add them together, you're just going to get x1 plus x2 times 1, 2, 0, and z1 plus z2 times 0, 2, 1. So you may want to write that out and do it as an exercise. Then we have the closure that's even simpler. So if x, y, and z is in P, then A times it is just AX times this vector plus AZ times the vector, in which case the scalar multiple is also in P. Okay, so the other axioms, you may want to check through them, but they pretty much inherit the various associative and distributive and the commutative property. They all carry over because P is a subset of, in this case, R3. The example we have here is very similar to the one from the previous slide, except now we have a subset of R4 that obeys this property here. We can rewrite this property as x4 equals the sum of x1, x2, x3. We can plug that in to our 4 tuple, so I've done here, and then we can take out the term that has an x1 in it, so it'll be the first position and the fourth position, and then we can add that to the term that has an x2 in it, the second and fourth position, and then the same for x3 in the third and fourth position. And so every element of this set H is a linear combination of these three vectors. And I'll leave it as an exercise to prove that this is a vector space, or a subspace, I should say, of R4. You can see some of the properties are pretty easy, like the zero vector is obviously an element of H because you could just take x1, x2, and x3 equals 0, and you get the zero vector. The associative properties, the commutative property, the several of the distributive properties, they all inherit because H is a subset of R4. And I'll leave the other ones for you to verify as an exercise. So just in general, in terms of terminology, if you have a subspace that's dimension 1 less than the containing vector space, that's called a hyperplane. So in our case here, we had a three-dimensional space, this set H, within R4, so that's a hyperplane. But you can go up to higher dimensions. You could have a subspace of dimension n-1 in n-dimensional Euclidean space, and that would be called a hyperplane. We have another example here. I'll leave this as an exercise for you to think through it, but the set just containing the zero vector is always a subspace of any vector space. Then a couple more exercises here. These are in a similar vein to what we talked about in the examples in the two previous slides. So here you have a subset of R5, and it has this property here, and you want to show that that's a subspace of R5. And then another exercise would be you have a subspace of R4 where this property holds, and in fact it's not a subspace of R4. So your task here is to figure out why that's the case. And I'll give you a hint. It has to do with the zero vector. Okay, so have a look at those, and hopefully this will help you get a better feel for the definition of a vector space when you go ahead and verify that, well, these two are in fact subspaces and this one is not. There's an easier way to show that a subset is a subspace of a vector space or not, and I held off in showing this until now because I wanted to give you a little bit more experience working through all the axioms. But the typical way we do this is that we need to show closure for both the additive and the multiplicative, scalar multiplicative operations, which you can kind of do on one step here, which I've shown here, where you have two scalars, A and B, and two vectors. If you can show this linear combination is always within your set X, then you have shown the two closure properties. And it turns out from this theorem that means that you have a subspace of V. And of course, if this doesn't hold true, then you don't have a subspace. So let's look at a proof of this. If S is a subspace of V, all linear combinations of vectors in S are also in S. This follows from the two closure axioms. That was the first and sixth axioms in the list. So that's easier going in this direction, but going the other direction, and this is really what we want to make use of. Assume S is closed under linear combinations. So if you take U and V and S and any two scalars from the field, in this case R, then the linear combination is in S. So assume that's true. So that immediately gives us the two closure rules, axioms of number 1 and 6. Axiom number 4, we have that from just taking the scalars being 0 and taking the same vector, or we could take different vectors. I took the same vector u, and so you have 0u plus 0u, and we proved earlier that this is, since these are in our vector space, these both equal 0, the 0 vector, and then when you add the 0 vector to itself, you get the 0 vector. So that proves that you have the 0 vector. Then if u is in our S, we can multiply it by minus 1. So again, we're using this property here. We just have minus 1 times u plus 0 times v, if you like. And that would equal minus u, and that's in S by this property here. And so that's the fifth axiom. And then the other axioms are the associative law for addition, the commutative law for addition. Then there's several different distributive laws, and they all inherit directly from S being a subset of V. And so there we have it. I'll give you an example in the next slide where we use this easier approach in proving that we have a subspace of a vector space. As another example, let's take the set of 2 by 2 matrices of the form shown here. We have x, y, z, and then, which could be any value from the real numbers, and then 0 here at the upper right. And in addition, x plus y minus z equals 0. So if we write z as x plus y and plug it in here, as I've done here, we can write any element of M in this form, x times this matrix here plus y times this matrix. And you can see that by just multiplying x here and y times this and then adding them, and you'll come back to this here. So to make use of theorem 2 from the previous slide, to show that M is a subspace of the vector space of all 2 by 2 matrices, we need to show that M is closed under linear combinations. So we take a linear combination of two elements from M, A plus x sub 1, y sub 1, z sub 1 plus b times x sub 1, y sub 2, y sub 2, z sub 2, 0. We do that, then we plug in, we write these, I should say, in this format here. So we have a times all this, b times this. And then we can collect things together. We have a x1 times this matrix and b x2 times this. So we get this here, and then we have a y1 plus b y2 times this here. And as we can see, it's a linear combination of these two vectors again, because this is a scalar and this is a scalar. So it's in M, and we've shown closure under linear combination. So M is a subspace of the vector space of all 2 by 2 real matrices. The span of a non-empty subset S containing vectors S1, S2 up to Sn of a vector space is a set of all linear combinations of vectors from S, which I've drawn out in detail here. So you have your n vectors and then scalars a1, a2 up to an. So if you take all possible combinations, linear combinations, that's what's called the span of S. We have a special case here. If you have an empty set, an empty subset of your vector space, then we define its span to just be the zero vector. And we've seen this idea in several of our examples. I point to example 3, but we've seen it in a few places where we were able to find the set of vectors that made up a subspace. And we also have a theorem here. The span of any subset of a vector space is a subspace of the vector space. And conversely, every subspace is the span of some set. We'll prove that on the next slide. We have two cases here. The first case is where our subset of the vector space is empty, and by definition it's just the zero vector. We mentioned that in the previous slide, and that's the trivial subspace. The more interesting case is where S is not empty. Then by theorem 2, we only need to check that the span is closed under linear combinations of pairs of elements. So we can do that pretty easily. We take two vectors from our span, v and u, and they can be written in this format here by definition. And then we take a linear combination of, or any linear combination of u and v. So we have x, v plus y, u, where x and y are scalars. We write that out here. And then you can collect terms. The S1 has coefficient x, a1, y, b1. And S2 has x, a2, y, b2 as coefficient, and so forth. And so this is just a linear combination of the vectors S1 to Sn. In other words, this linear combination is in the span of S. So we can also go in the other direction. If the vectors of a subspace span the subspace, that's pretty obvious because you can always write a vector in the subspace as just 1 times itself. It doesn't span anything more than that because of the closure axioms. So in fact, the vectors of a subspace exactly span the subspace. The tricky part here, or the question here, is that what we really want to find is a minimum spanning set for a subspace, and that's not typically all of the vectors in the subspace, as we'll get into that later. Theorem number 4. The span of a subset S of a vector space V is the smallest subspace containing all of the members of S. So from theorem 3, we know that the span of S is a subspace of V. But we also need to show that it's the smallest. So let W be any subspace of V that contains S. We want to show that span S is a subset of W. So since W is a subspace and S is a subset of W, W must contain all linear combinations of vector and S because subspaces are closed under linear combinations. Thus, the span of S is a subset of W. So what we've shown is that the span S is contained in every subspace that contains S, making it therefore the smallest subspace containing all the members of S. We have a couple more examples before we close off this lesson. In any vector space V and vector V in V, the set L equals A times V, where A is any element of the real numbers, is a subspace of V. This follows from Theorem 3 since L is by definition the span of V. We can think of L as a sort of generalized line, and we've already seen an example along this line before. The span of vectors 1, 0 and 0, 1 is all of R2. We can easily see that. If we take any vector x, y, and R2, we can write it as x times 1, 0 plus y times 0, 1. So a couple of questions which we'll get to in the next lesson. Is 2 the smallest number of vectors that span all of R2? Assuming the answer to the first question is yes, are there any other pairs of vectors that span R2? This has to do with something called linear independence, and we'll get to that in the next video.